plus 2. Dear students, today we are going to deal with preparation methods of ethers. Before starting with that, like the channel, subscribe it and share it with your friends. Hit the bell icon to get the notification. Let's begin with it. Methods of ethers. We are going to deal with first dehydration of alcohols and from alkyl halides by Williamson synthesis. Let's see the reaction in detail. First, by dehydration of alcohols. Alcohols undergo dehydration in the presence of protic acids like H2SO4 or H3PO4. The formation of product alkene or ether depends on reaction condition. Now how the reaction is taking place, let's see. Here this is ethanol. Ethanol in the presence of H2SO4 at 413 Kelvin, it requires 2 ethanol molecules. As you can see here, water molecule is removed and formation of ether is taking place. Here the ether formed is diethyl ether plus water. Primary alcohols are used to get symmetrical ethers. When ethanol is treated with H2SO4 at 443 Kelvin, formation of alkene takes place, that is ethene. Use of high temperature or secondary or tertiary alcohols gives alkenes. In this way, alcohols in the presence of protic acids, that is H2SO4 or H3PO4, the formation of product, that is alkene or ether, depends on the reaction conditions. Let's see how. This is an ethanol. Ethanol in the presence of H2SO4 at 443 Kelvin forms alkenes, whereas at 413 Kelvin it forms ethers. Preparation of ethers from primary alcohols is much suitable, while from secondary and tertiary alcohols it undergoes elimination to form alkenes instead of substitution. Preparation of mixed ether is possible using 2 different alcohols, but they are difficult to separate. Three steps. In the first step, formation of protonated alcohol is taking place. Let's see how. Here, this is an alcohol. As we find here, oxygen atom carries 2 lone pairs. So hydrogen with positive charge forms a bond with the oxygen atom and protonated alcohol is formed. This step is the fast step. In step 2, nucleophilic attack of alcohol molecule on protonated alcohol from the first step can be seen. This is alcohol molecule and this is the protonated alcohol from the previous step. Nucleophilic attack of this alcohol molecule on this protonated alcohol is seen in this step, as it can be seen shown by the arrow. This is the slow step. In the third step, deprotonation to form an ether is seen. The product formed in the second step, it is found that this hydrogen atom gets removed, and this is a very fast step, giving rise to formation of ether due to breaking of OH bond. In industrial method, it is used to prepare millions of gallons of diethyl ether. Williamson synthesis. This is the method of preparation of ether from alkyl halides. When an alkyl halide is heated with alcoholic sodium or potassium alkoxide, it gives corresponding ethers. May be simple or mixed. Let's see how. RONA is sodium alkoxide. This is sodium and this is alkyl group attached to oxygen. So it is sodium alkoxide. When it is treated with alkyl halide, that is RX, NaX, which is highlighted part, gets removed, and this R, that is alkyl group of alkyl halide, forms bond with the oxygen atom to form ethers. And NaX is removed. Let's understand it with example. Sodium ethoxide, when treated with ethyl bromide, NaBr is removed and this C2H5 forms bond with oxygen atom to form diethyl ether, and NaBr is removed. Ethers containing substituted alkyl groups, that is secondary or tertiary, may also be prepared by this method. To prepare ethers, alkoxide and alkyl bromides with different alkyl groups are to be selected. This is how to prepare ethers. Let's understand. Reaction of methyl bromide with sodium tertiary butoxide. Gives exclusively tertiary butyl methyl ether. How it happens? Let's understand. Methyl bromide when treated with sodium tertiary butoxide, as we can see here, NaBr is removed and methyl group forms bond with the oxygen atom. Thus, tertiary butyl methyl ether is obtained and NaBr is removed. Better results are obtained if alkyl halide is primary and alkoxide is tertiary. If a tertiary alkyl halide is used, an alkene is the only reaction product. For example, reaction of sodium methoxide and tertiary butyl bromide gives exclusively 2-methyl propene. This is tertiary butyl bromide, that is tertiary alkyl halide. Treated with sodium methoxide, it undergoes beta elimination to form alkenes. So 2-methyl propene, NaBr is removed and methyl alcohol is obtained. It is because alkoxides are not only nucleophiles but strong bases as well. They react with alkyl halides, leading to elimination reactions. Let's see how Williamson synthesis is seen in phenols. Phenols are also converted into ethers by this method. Here this is phenol. When it is treated with NaOH, it forms sodium phenoxide, which on treatment with alkyl halide, as we can see here, R forms bond with oxygen atom and Na forms bond with X. Thus, formation of ether is taking place. Let's see here. Phenol, when treated with NaOH, forms sodium phenoxide, which on treating with methyl iodide forms anisole and NaI is removed. Physical properties of ethers. Physical states and boiling point. Here we see this is dimethyl ether. And here this is ethyl methyl ether. Dimethyl ether and ethyl methyl ether are gases. Other ethers are colorless liquids with pleasant odor. Lower ethers are highly volatile and highly inflammable. And boiling points of ether. Boiling point of ethers show gradual increase with the increase in molecular mass, as it can be seen here. As the molar mass increases, we find the boiling point gradually increases. Not 180 degrees. but it shows a small net dipole moment, that is 1.18 dB for diethyl ether. Here the bond dipole moment of the two CO bonds CO and CO do not cancel each other, and therefore ether possesses a net dipole moment, as in case of diethyl ether. Weak polarity of ethers do not affect their boiling points, which are about the same as those of alkanes having comparable molecular mass. Here, the dipole moment of two CO bonds do not cancel each other, and hence a net dipole moment is seen. The bond angle in ethers, that is COC bond angle, is 110.3 degrees. Ethers are slightly higher than that of alkanes, but much lower than that of alcohols. As it can be seen here, this is an alkane, the bond line formula. This is an ether, and this is an alcohol. As it can be seen here, the boiling points vary. This contains 5 carbon atoms, whereas this contains 4 carbon atoms. If we increase the number of carbon atoms to 5, the boiling point will be higher, slightly higher. Large difference in the boiling point of alcohols is due to the presence of hydrogen bonding in alcohols. Like alcohols, oxygen of ethers can form hydrogen bond with water molecule. The intermolecular hydrogen bonding, which holds alcohol molecules together strongly, is not present in ethers. The CO bonds in ethers are polar and thus have dipole moment. The weak polarity of ethers do not appreciably affect their boiling point as compared to alkenes, but are much lower than the boiling point of alcohols, as it can be seen here. Here this is N-pentane or normal pentane. This is diethyl ether and this is butan-1-ol. We can compare the boiling point of each of these compounds. This comparison is seen showing the boiling point in such a way because solubility of ethers in water is similar to that of alcohols of comparable molecular mass. And this is because ethers can form hydrogen bonds with water through the ethereal oxygen. Dear students, if you like the way of presenting, please subscribe my channel, like and share it with your friends. Thank you.